one such is a counter. We had been off and on talking about a counter for long, but we should know how a counter should be designed. And then there are some special kind of counters that does not necessarily count from, let's say, the way we count 0, 1, 2, 3, 4, whatever, right? They might have a specialized sequence, or they might have a specialized pattern. Okay, so even this Tesla tail light example that we have done is some sort of a counter, right? It has a specific counting pattern, right? And then it loops back. Okay, so typically counters can be classified as an up counter and a down counter. For a regular counter, if it counts upwards, let's say 0 from the lower value to a higher value, it is called an up counter. So up counter counts from lower to higher value. Okay, whereas a down counter is for higher to lower value. Okay, but it could be also some other sequence that you have been given to produce. That is what you have to do. But the principles that we have already taught, they are not going to change. Okay, so one more thing that I would let you know is the kind of designs that we are practicing in this particular course are called synchronized sequential circuits. Okay, there is another branch of this particular discipline where we also investigate design of asynchronous sequential circuits. So what I mean by synchronous sequential circuits is that if you have this collection of the flip-flops, right, you have some collection of flip-flops in the system, right, and you have some kind of an output and input to the system, right? There is an input, there is an output to the system, this also goes back and so on. Apart from that, what is important is that you also have a clock, right? You can have some memory element also here. Anyway, so what is also important is there is a clock. Okay, so this clock for a sequential circuit has to be given to this individual flip-flops, because those flip-flops could be edge triggered, and on the edge of the clock they are going to fire, right? Whatever is the value, depending on the kind of flip-flop, depending on the output, depending on the previous state, it is going to change its state, whatever we call it the next state. Okay, for synchronous sequential circuit, you need to remember one important point, that this clock has to be the common clock. This clock has to be the common clock that is provided to everybody. Okay, so this is called a synchronous sequential circuit. In case of asynchronous circuit, right, so this blue color here, I am writing this note, right, this is more of a synchronous design. Okay, but we can also have circuits that we are not going to cover much in this course, is that I am doing dotted lines. So the clock could be given to this particular circuit and maybe this particular circuit. So the outputs of this clock, outputs of the these flip-flops which are directly connected to the clock, could be driving the clock inputs of the other circuits, right? So if I have A and B which are directly driven by the clock, A's output could be used as a clock input to C, right? And maybe B's output is used for a clock input to D. Okay, maybe C's output or maybe D's output is used as a clock input to E, and so on, right? So in this case, what happens is that not all the circuits or not all the flip-flops are going to be triggered at the same time as the main clock, right? Because the clock that the other flip-flops are getting, or the edge triggers that the other flip-flops are getting, are a function of how they are interconnected among each other. Okay, so that is called a this is a dotted line async design. Okay, so in most of the design that we are going to look at this particular course are going to be synchronous sequential circuit. This is a very important point that you need to remember, because the circuit behavior is going to completely change if you are using an same thing, but your clocking is not synchronous, but the clocking is asynchronous. It is going to be very, very different characteristics. Okay, so here we are trying to analyze and build clocked synchronous sequential circuits. Again repeating that the clock has to be the same clock that is distributed to the clock inputs for every flip-flop. Okay, and your sequential circuit is going to have a collection of flip-flops only, right? It could be JK, it could be D, it could be any other thing, right? Okay, so let us try out this particular exercise where we want to do a counter design. Okay, synchronous counter design, and we can always do this thing with a JK flip-flop as well as a D flip-flop, right? So D flip-flop, as you know, that if you put a data D on the flip-flop, in the next clock pulse the output will be the same as the data, right? So we have already studied set reset, data, write enable. If you have the write enable to be allowing inputs, right? If the write enable is 0, then it's going to have in a memory hold state. But assuming that the write enable is 1, that you are trying to write to the output of the flip-flop, whatever data you put in the input, that is the same thing that is going to be appearing after a certain delay. Okay, delay means 1 clock delay. That's why it is called a D flip-flop. So this is a 3-bit down counter, right? Let us see how to create a design for this kind of a problems. Okay, so as I told you, you should always start with something called a initial state, or initial state is the first state, but at any point in time there is a concept of current state. Okay, so if I am in certain state X, what should be the X next? Okay, so let us write down that I should have a part of the table that encodes my current state. Current state. Okay, and this current state has to be encoded. We will come to that. Are there any inputs to this system? No, right? If there was an input to the system, we could have thought maybe that input to the system, we can discuss it later, could be itself whether it wants to count up or count down. That could be an input, right? So if somebody presses please count up, it will count up. If somebody presses count down, it will immediately start counting down, right? So we are not considering it right now here. It's just we'll stick to a simple 3-bit down counter. So after current state, you should have the next state. And then you should have the next state logic, right? Which is nothing but the flip-flop inputs. Okay. So now let us look into the thing that has been asked. It is basically trying to design a 3-bit down counter. So it has already mentioned that there is this 3-bit, right? And you should have 8 states. So there is no really bit savings that we can do here. Okay. So the current state is going to be anyway Q2, Q1 and Q0, right? The next state could be also defined as Q2 plus, Q1 plus and Q0 plus. And the next state logic is going to be the function that we are going to put, function of Q2, Q1 and Q0 that we are going to put to the inputs of the flip-flops. So there are 3 flip-flops we are going to consider, because there are 3 bits that we are dealing with. So there could be D2, because it's a D flip-flop, we have to use only one input, and we are assuming that write enable is on, right? We are allowing, otherwise it doesn't make sense. It will only be in a memory hold state. D1, and D0. If it was asked that you would want to do the design using JK flip-flops, then you should have 6 inputs, right? Because every JK flip-flop are going to have 2 inputs. So in that case, it would be J2, K2, J1, K1, J0, K0 and so on. Okay. So this is going to be the design. So now if I want to let's say design a down counter, and for simplicity I'll start with 7, right? Because 1 1 1 I want to go down, right? It does not mean that it has to be the initial state, because it's cycling. If I started with 0 0 0, that is also fine. So what should be the next state after 0 0 0? After next it should go to 7. That's all, right? This is cyclic, it doesn't change. I am just doing it for your own understanding first time. So 1 1 1 is 7. What should be the next state after 1 1 1? This should be 6, right? So 6 is going to be 1 1 0. So let us first complete the state transition table. I can first understand the sequence of states, how they are flowing, and then we will try to implement the next state logic. Okay. So if it is 6, which is again 1 1 0, what should be the next state in a down counter? The next state in a down counter should be 5. So 5 is 1 0 1. If it is 5, the next state should be 4 1 0 0. If it is 4, the next state should be 3 0 1 1. If it is 3 0 1 1, the next state should be 2 0 1 0. If it is 2 0 1 0, the next state should be 1 0 0 1. If it is 1 0 0 1, the next state should be 0. Note that we are not done yet, right? I told that 7 to 6 to 5 to 4 to 3 to 1 to 0. But you need to make sure that this counting sequence is cyclic, right? Because once it reaches 0, it's expected to, if that is one of the design requirements, we are assuming that that's a design requirement. So it should count to 7 to 0, and then be again, it should go to 7, right? That's a part of the current state, next state relationship. Okay. So if you reach 0, because the system won't know, suppose I reach 0, what to do next has to be told to the circuit, right? So you can say, no, I want to go to some, I want to go to 6, right? That is your choice. But in a sequential circuit design, you need to explicitly state that what state leads to what state, right? So otherwise the circuit will go to some other random state, because we are not designing the circuit for a given behavior. Okay. So if I want to explicitly mention that 0 0 0, it should be followed by 7. Okay. Then it becomes cyclic, because 0 to 7 again this loop starts. It comes to 0 and again goes back. Okay. So this is what is called the current state and the next state relationship. Okay. And in case of a D flip-flop, right, you know that if this is a D flip-flop, of course there is a clock, there is an input and there is an output. If we put a clock input, the input is going to, if we put a H trigger, basically, if there is an X, this X is going to be copied here. Okay, there is nothing fancy like a JK flip-flop that has a set reset as well as a toggle condition. Okay, or like a memory hold, nothing like that. It can either clear off or it can put it to 1. So I can pass X equal to 1 or I can pass X equal to 0. If I pass X equal to 1, in the next, after the clock, the next output will be 1. If I put X equal to 0, after I put the clock, the output is going to be 0. Okay, so as simple as that, which is nothing but the copy of the next states, right? If Q2 is 1, D2 has to be 1, right? Because there is no other alternative. If D2 is 1, then only after the next cross plus Q2 plus will become 1. So you have to be simply do nothing but is just copy and paste of this particular sequence of actions. So Q2 plus Q1 plus Q0 plus should be D2, D1, D0. Okay. So 1 0 0, 0 1 1, 0 1 0, 0 0 1, 0 0 0 and 1 1 1. Okay. So if we want to design this particular circuit, we have to, the next thing that we have to do is that this is a next state logic, right? According to these inputs, but this has to be designed. Okay, we have not yet designed it. We have to find out the SOP or use a K map or something and simplify this, right? If we want to simplify, it's not necessary that you have to simplify, but if you of course want to have an optimized implementation in terms of the number of gates, it's better that you simplify. Okay, but to understand the concept, we don't have to do anything more other than having a function. So for D2, with function for D1 and a function for D0, which could be as well as even be the SOP. Okay, you can just look at the mean terms, and for every such mean term you can associate you can add them, right? Wherever there is an 1, you can just simply find out the SOP expression, and or you can simplify them. Okay, so that I will leave to you as an exercise, and I will do maybe I'll try doing at least one of that. So let us see that how to just do this. So you should draw the K-map table, right, where you should have, let's say this is Q, let me see, I have used Q0, Q1, Q2, right? So this could be Q0 and this could be Q1, Q2, right? So you can have 0 0, 0 1, 1 1, 1 0. Note that this is in a gray code format, and this could be 0 and 1, right? And then we can also do this. Okay, and you have to tell me that you are designing the circuit for a certain function. Let us say this is, we are trying to design for D2. Okay, so we are going to do the design for D2. You can similarly do it for D1 and D0. That's a part of the simplification. So now let us identify the cells where let us identify the cells where we are going to have the value or choose this particular mean terms, right? So this is this one, this one, this one and this one. So there are 4 things, right? So the first thing is 0 0 0 for D2. Okay, let us tick mark 0 0 0. So this is your 0 0 0. Then let us look at the next 3 we have. So the top one is 1 1 1. Oh, top one is 1 1 1. So 1 1 1 should come here. Then we have 1 1 0. Okay, so 1 1 0 is Q1 Q0 is 1 0, Q2 is 1. So Q1 Q0 is 1 0. So Q1 Q, oh sorry, so this is 0 we have taken separately. So Q1 Q2 we have to see. So Q2 Q1. Okay, so Q1 Q2 should be 1 1. So Q1 Q2, if you see, this is 1, this is 1. Q1 Q2 should be 1 1 and Q0 should be 0. Okay, so both are 1 and Q0 should be 0. Then the last one is Q1 Q2 should be 0 1 and Q0 should be 1. So 0 1 is here and this should be 1. Okay, so Q0 is 1, Q1 is 0 and Q2 is 1. The same thing that we have done, and you can of course do the simplifications the way we typically circle these terms out. This is one that you can do, this is the other one that you can do also. So in this particular example, in the vertical one, Q0 is going to definitely vanish, right? And this is going to result in Q1 Q2 In the other one, as we can see, Q1 is going to vanish because this is 0, this is 1. Q2 is going to remain, and Q2 and Q0, because this is 1, this is Q0 and this is Q0 bar, and the other single one is Q0 bar, Q1 bar, Q2 bar, right? So this is going to be a simplified expression for D2. Similarly, you can solve for D1 as well as D0. So repeating the design that we have already seen, this is going to be a synchronous sequential circuit. So you should have these 3 flip-flops. Okay, this could be represented as the D flip-flop 0, this could be D flip-flop 1, this could be D flip-flop 2. The next thing that you have to give is a synchronous clock pulse. So this could be the clocks, right? And you need to make sure that the clocks are simultaneously applied to all of them. So this is your clock. Now you have an output. So these are your outputs. So maybe I'll draw your outputs with a different color. So these are your outputs. This output is indicated by Q0, this output is indicated by Q1, and this output is indicated by Q2, right? So we have designed the function for D2. So here you should actually put this function of D2 as a function of Q1, Q2 and Q0. Okay, Q2, Q1, Q0, and we have the function. The function is nothing but this. Okay, so Q1, Q2 plus Q2, Q0 plus Q0 bar, Q1 bar, Q2 bar. Okay, so I have a implementation of this particular circuit, and here you can see this is D2, right? D2 has this 2 things. One is this Q0 bar, Q1 bar, Q2 bar, right? You can see these are your inverted inputs, right? Here also this is an inverted, this is not the Q, not the top one, but the bottom one, which is the inverted one. This is also the same thing, inverted one. So this basically is that thing, right? And here you are going to have, I guess this is Q, this is the Q0 one. So this could be Q0, Q2. This could be probably Q0, and because Q2 should have a feedback, right? So this is Q0, Q2, and the other one should be Q1, Q2, right? This should be probably Q1, Q2, and you put them to the OR gate and you pass this input. So this is basically your input state logic, or the combinational logic that is being fed to the last flip-flop. Okay, similarly you have to design the functions here. Okay, function for D1, function for D2, D0, and so on, right? So this is going to be working the way we have specified. So we have specified it to work like this, that it has to follow this cycle from 7, 6, 5, 4, 3, 2, 1, 0 and back to 7. Okay, and we have kind of understood the complete way how to design such circuits using a given kind of a flip-flop, right? So I showed you one of those expressions. You can simplify the other expressions. Okay, and it comes out to be, I could see an XNOR, right? So this is an XNOR function. This is probably very simple, D0. I could see this is just probably Q0 bar, right? This Q0 bar is being fed, right? You can simplify it and figure it out. Okay, so now you can see that I can make this circuit work, and you can see that this is following a certain pattern, right? 6, you have to count it from the other side. Okay, this is 5, this is 4, this is 3, right? So this is the most significant bit, this is the most significant bit, this is the least significant bit. Okay, we are normally used to look at bits the other way around, okay, but I can explain you that if you just follow, this is 4, right, 0 0. So now whatever is being shown in the screen is not 1 but it's 4. MSB is 1, LSB is 0, the middle bit is also 0, okay. So this is 4. So you can just check this thing one more time and you will get a better understanding. So I can drag it to some place, right, and you can see the output. Here the output is actually 1, okay. MSB is 0, the middle bit is 0, the least significant bit is 0, right. So I could have drawn the circuit the other way around. I could have made D2 on the left hand side and D0 is the on the right hand side. That is my fault, but D0, D1 and D2 are specified and MSB and LSB specified. So technically there is no problem, okay. So what will be the next state after this? Everything is going to be off because this is representing 1, so it should become 0, okay. So it is 0. After 0 it should go to what? After 0 it should go to 7, so 7. After 7 it should go to 6, so MSB should be 1, middle bit should be 1, LSB should be 0. That's what happened, okay, and so on, right. You can look at this, you can create this circuit rather in circuit verse and look at the different possibilities, okay. So after this I'll try to give you some exercises, okay, and you can come up with your own circuit verse based implementation and verify whether it is correct or not. And if you have any issues in designing the circuit, you can always contact our instructors, they can help you, okay, design this circuit. So the first one is I am asking for an n bit odd even synchronous up down counter. So up counter is a separate counter, down counter is a separate counter. It could be an odd counter or an even counter. So there are 4 designs that you can do, right. So suppose for question number 1 you want to do a let's say a 3 bit odd counter, odd down counter. What will be the counting sequence? The counting sequence is going to be 7 5 3 1, right, and back, okay. You can think whether you want to do it using 3 flip-flops or 2 flip-flops, let's say, right. Here the number of unique states is much lesser, but you know the recipe, right. Or if you want to do a 3 bit even up counter, okay, 0 2 4 6 and back. You can try this out, okay. Similarly you can do anything that you feel like, right. It could be prime counter and so on, okay. The other interesting thing which is going to be having a lot of different applications is a mod n counter, okay. So the mod n counter is going to count till n minus 1. So if I say that for the third kind of a design, design a 3 bit mod, let's say 5 counter. So in many applications we don't have to really count from 0 to 2 to the power n minus 1 because the number of bits are that much and it allows you to free flow from 0 to 2 to the power n minus 1. I might have a special requirement that I want to reset the circuit back to 0 at a certain count value. This has a lot of applications in processor design where I want to wait only for a certain number of clock periods, right, and maybe I'm executing some instruction. Some instructions take less time, some instructions take more time. If it is taking less time, I do not want to count till 0 to 2 to the power n. I want to reset it back and then start executing the next instruction. So there are implications, okay. So a mod 5 counter is going to be counting from it's a 3 bit counter, so it has the capability to count 3 bits. So this is going to be 0 1 2 3 and 4. So 5, 6 and 7 could be represented, but they are not going to be used. Okay, so these will be unused because you are using 5 states, right? 0, 1, 2, 3, 4. There are 5 states. You do not have the option to use 2 flip-flops. You have to use 3 flip-flops, and this is going to be the counting sequence and back. Okay, so this is called a mod n counter design. Okay, so this is also something that you can do either up counting or down counting depending on in what direction you want to count, but the formula or the recipe that you want to know from here is the same, right? That's why we kind of called you in the very first class. We told you that we are going to learn some design principles. So any kind of sequence that would be given to you, any kind of counter that is given to you, you should be able to design that using the simple recipe of this table, the state transition diagram table. Okay, so there is a current state, there is a next state, and given the kind of flip-flop that you want your design to be implemented in, it could be T flip-flop, JK flip-flop, D flip-flop, whatever be it, you should correspondingly look at the corresponding excitation table, and looking at the excitation table you find out that how the bit transition happened. If you know the individual bit transition that happened in every row, for every row you can actually fill up the corresponding logical input to the D flip-flops or JK flip-flops, so that will make that transition possible. That is what your excitation table tells you. So you should always, while designing this, you should have the excitation table in your mind. Excitation table should be at your fingertips. Okay, so without the excitation table you cannot find out this particular inputs, because the excitation table is a more primitive table that has been derived from the architecture of the flip-flop, right? The flip-flop has been architected in a certain way that for these inputs with the clock pulse, what is the output? The state machine for a given flip-flop is implemented by this excitation table or abstracted by the excitation table. So you need to have that. Okay, so even because these flip-flops are independent, it's just an extra thing that I want to add, right? So maybe you want to implement the middle bit using a JK flip-flop. It's possible, right? As long as you have a flip-flop, that is enough, right? It's an extra thing, but anyway, I just wanted to mention because we are already here discussing about it. So let's say the leftmost bit of D2 is represented by a D flip-flop. This is represented by a D flip-flop, but for D1 I do not have a D flip-flop anymore. I have a JK flip-flop, right? I can always design this internal the middle flip-flop using the JK flip-flop, and instead of D1 I should have J1 and K1. Okay, and nothing changes, right? That should only affect where. If I want to design the circuit using JK flip-flop instead of D1, you should only look at the output of Q1, that is only a JK flip-flop, right? So you should look at this particular column and this particular column and find out the outputs, right? For example, here it is a 0, right? It goes to 1. Okay, so it's a 0 to 1. It is basically a toggle or a set, right? So you have to look at the corresponding excitation table. Either you can, if you want to do a toggle, you can treat it as a toggle, so it becomes 1 1. If you want to set it as a set, then 1 and 0, right? So it becomes 1x. Okay, so in case of the J1 K1, you have to write 1x. Okay, so this is just an extra thing that I want to tell you, because the beauty of this synchronous sequential circuits is that all the flip-flops that you have are independently clocked. Okay, so if you want to have a certain transition from a certain current state to the next current state for a particular bit, you can independently do the design. Okay, In fact, you can have 3 kinds of flip-flops representing 3 bits. One could be the D flip-flop, one could be a JK flip-flop, one could be a T flip-flop. All flip-flops allow you to do a state transition. Either I want to hold to the current value 0 or I want to go to 1. That is always possible. Okay. JK flip-flop uses an additional advantage. For example, it can, without even knowing what is there, I can invert it, right? That is called toggle, right? But that is always not needed, right? I can have D flip-flop and achieve the same goal of designing this sequential circuits. Okay. So please try to implement this 3-bit counter or try out the design that I have told you, and it is heavily recommended that you not only try out a 3-bit down counter with D flip-flops, you also try out it with JK flip-flops. That will give you a little bit more practice. It is going to be a little bit more elaborate because 3 flip-flops with JK are going to have 6 inputs, right? J1, K1, J2, K2 and J3, K3. Okay. You should be practicing up as well as down and various kinds of things like a special sequence. So the special sequence could be 1, 3, 5, 6, 7, right? And then back. So as many kind of variations and variations you try out, you will have a better grip on the particular topic, right? So this is all about designing sequential circuits, and one particular example was the counter. We will also look at a few kinds of counters that are very special in the context of a computer processor, in particular ring counter and Johnson counter, that we will cover in the as a separate lecture. Okay.